right, so now that we have seen damped harmonic oscillation, we now want to do an example of this. So here we have a simple pendulum, which has length L with a bob attached to it of mass M, which is moving in oil. Okay, so this thing is going to be moving and it's going to feel a resistive force, where we're told that the magnitude of this resistive force is equal to 2m times the square root of g divided by L times L times d theta dt. So this thing is linearly proportional to the velocity at which this thing has, the angular velocity. And what we're looking for then is, under the initial conditions, that the initial position of this thing at time 0 starts off at some theta 0, and then that the velocity, angular velocity this thing has is 0 initially. So here we want to find the angular displacement and the velocity as a function of time. So here what I want to know is what is theta as a function of time, and what is the velocity as a function of time as well. And then we want to make a sketch where here we're going to use the parameters that g divided by L is equal to 10 radians per second, and that the initial angle is equal to 10 minus to the minus 2 radians. And we're going to work under the fact that this thing has small oscillations. Okay, so this is harmonically oscillating back and forth, but under small oscillations. So good, so here I'm assuming that the velocity is in this direction, so this is d theta dt, which is why the resistive force is in the opposite direction. So good, so from here we can look at what? The net torque on this guy. So first of all, we know that the net torque, so that's right, the sum of the torques is equal to the moment of inertia times then the angular acceleration. So here we have the portion of gravity pulling it back. So as we talked about before, this is then minus mg sine of theta times the distance at which this is acting, which is at the distance of L. But then we also have this resistive force. So the resistive force then is going to be minus 2m square root of g divided by L times d theta dt. And all that's equal to the moment of inertia. Now, since this is a massless string, that means it has no moment of inertia. The only thing that has moment of inertia is the bob, which means that's a point mass. That's moment of inertia is simply the mass of it times the radius it is away from the origin squared. In this case, is just the length of the string, times then the angular acceleration, which is the second time rate of change of the angular position. Good, so from here, let's divide everything by mass, so that term's going to go away. Let's divide everything by L squared. Oops, forgot that L there. So this L is going to go away, this L will go away. So ultimately, this thing is going to become what? The second derivative of the angular position plus then 2 times, make sure I get this thing correct. That's just a simple L, right? Yeah. Good. Times then, so this should give me a square root of g divided by L times d theta dt plus g divided by L times sine of theta, but again, we're going to work under small oscillations, so we're going to call that guy simply equal to theta. So good. So good. So basically from here, what we can see then is that our damping parameter is this term. So matching this to what we just did, so we can see that beta then is equal to the square root of g divided by L. And then from here, we can see the natural frequency squared is simply g divided by L, which means that omega 0 is equal to also the square root of g divided by L. Which basically means that these two things are equivalent, which means that we are in the critically damped phase. So, using what we just talked about, what we know in this case then is that what? These things, that our general solution is going to look like the following. So since we have critically damped, in this case we know that theta is a function of time, then it's going to be equal to some coefficient C1 plus another coefficient C2 times time times e to the minus beta times time. Now from here, to determine these coefficients, we then have to use our initial conditions. So before we do that, let's consider the derivative of this guy. So it's going to be the same thing then as what? So we have the product of two functions, this times this. So I'm going to get a minus beta times e to the minus beta t times c plus c2 times t plus derivative of this guy, which is simply going to give me a c2 times e to the minus beta t. So that's him. So now let's use our initial conditions. What we know then is that the initial position of this thing at time is equal to 0 is equal to theta 0. So here this term is going to go away, this term is going to become 1, so this means C1 is simply theta. Our initial condition is that the velocity evaluated at time is equal to 0 is equal to 0. So from here, oops, this term then is going to go to 1, this term is going to go away, and this term is going to go also to 1. So in this case, we're then left with what this is equal to minus beta times C1 plus C2 is all then equal to 0. So from here, this tells me C2 then is equal to simply beta times C1, which is the same thing then as beta times theta initial. Because according to here, C1 is then equal to theta initial. So good. So putting everything together, what this means then is we can rewrite this as these lines. So my position as a function of time, or the angular position, is going to be equal to theta initial plus beta times theta initial times time, all times e to the minus square root of g divided by L times time. Or I can factor out that theta initial, so it's going to be the same thing then as what theta initial times 1 plus beta times time, e to the minus square root of g divided by L times time. And then my velocity as a function of time is then equal to, so minus beta e to the minus beta times time times theta initial plus beta times theta initial times time plus beta times theta initial times e to the minus beta t. So from here, we can then factor terms, combine things together, but we finally get, in this case then, is that what? Good, so this becomes equal to, so once I cancel out terms and do all that good stuff, this thing works out to be minus g times theta initial divided by the length times time, e to the minus square root of g divided by L times time. So the next thing we want to do then is simply make a sketch of the phase space diagram for this using those particular values. So good. So our phase space diagram is going to look like this. So here I'm going to have d theta dt. Here I'm going to have theta. So again, what we know is initially this thing starts off with 0 velocity. When he is equal to 0, so this thing is actually going to, what? We have 0 velocity when this thing is at, what, 10 radians per second, with the initial angle of 0.01 radians. And then this thing is going to end up doing this. So this is our phase space diagram. So good. So this was an example of damped harmonic oscillations. So the next one we're going to look at is what happens when our system then injects, or we inject energy into our system to try to keep this thing to have constant energy, which means we're going to look at what are known as forced or driven harmonic oscillators. So in that case, we want to inject energy into the system at the same rate at which energy is being lost into the medium itself.